talk about the exam problem. Since if I broadcast, the whole contents, time, the elapsed time is so long, like more than 1 hour. That's why it makes students very hard to follow the lecture. That's why I break down the lecture into small units for you guys, so that later you can navigate between the different subjects to find out the information that you want very easily. That's why. Okay, this is a temporary wood dam problem. For example, this is the top view. This is the top view of the wood dam, and then this is the side view of the wood dam. Okay, and then make sure that we have water here. And then because of water, if in this example problem, the water is filled, where is it? And then the part is crowned the cantilever beam. It says it's a cantilever beam. It is supported here, and then the water level behind the dam is full height. H is 2 meters. So it says that this is 2 meters. So I told you that we'd better use the millimeter units, isn't it? Okay, 2 meters. And then say, because this is water, and then there is a pressure field, isn't it? So the pressure, the distribution of pressure is what? The specific weight of water times the height, the position. Let's say if let's put the x coordinate, it depends on the x coordinate. On top here, the pressure should be equal to 0. So h minus x. So for example, if x is equal to 0, the pressure is maximum. And then if x is equal to h, the pressure is equal to 0. So the pressure distribution is linear, should be linear here. And then here, look at this. So we have self-similar structures here. Then pressure, the pressure is, applied to the horizontal planks, and then the force, the pressure applied to the flank is transferred to this beam here. Okay, so all other dimensions, for example, spacing is given as 0.8 meters, like 800 millimeters, but the size of the cross section, is not given. So we have determined the minimum required dimension of the post, and the allowable the bending stress is given here. So now let's talk about the beam problem, the dam problem a little bit more. Let's imagine that we have a dam problem. Okay, this is a dam. And then if you consider distribution of the pressure, then what? So it should be resisted by the horizontal force here on the bottom, and then the bending moment, isn't it? So this is nothing but just the beam problem. So it can be changed to the cantilever. And then we have horizontal force and then bending moment. You understand? Okay. So if you consider the force equilibrium, you can easily determine the bending moment and the horizontal force. So in this case, the level of water is here. But let's consider some other cases. If you consider other types of beam problem, the dam problems, though sometimes we have overfill. So if you have overfill of dam, the water level would form like this, isn't it right? So in this case, on top of the dam, the pressure field would form like this. So pressure is equal to 0 at this point, but we have non-zero pressure on top of this dam here. So in this case, the problem can be simplified to this way. So moment increased by this. That's why if we have excessive overfill in dam problems, then that would cause collapse of the dam. So probably you understand the situation now, right? So now let's go back to our exam problems. In our exam problems, we have, okay, let me sketch the problem so that you can understand the problem easily. So we have flank here. Okay, we have plate. And then it is bottom here. And then it is subjected to water pressure. So what's the maximum pressure value here? P max is equal to the specific gravity of water times the depth. The depth is given by 2 meters, 2000 millimeters. Then let's try to calculate it. So specific weight of water is what? Gamma W is 1000 kilogram force per cubic meters, isn't it? So if you change it to the Newton unit, 1000 times 9.81, the gravity acceleration, divided by 10 to the power of 9 millimeter cube, isn't it? So you can calculate the specific weight of water. Or simply, if this calculation is complicated, so we can use kilogram per meter to calculate maximum pressure. The maximum pressure in the unit of kilogram force and meter, then 1000 kilogram force divided by cubic meters times 2 meters is equal to 2000 kilogram force per meter square. Okay, so let's change it to the megapascal unit. So if you change it to megapascal unit, then let's change it to megapascal unit. So the maximum pressure P max is equal to 2000 times 9.81 divided by 1 million millimeter square, and this is Newton. So this is equal to, if I calculate it using my Excel spreadsheet, then 2000 times 9.81 divided by 6. This is around 0.02 0.020 megapascal. So this is the maximum pressure. And then this plank is supported by a post here, isn't it? The spacing of post is given by 800 millimeters. The spacing here is 800 millimeters. So for individual spacing becomes a cantilever. So we can consider this as cantilever, isn't it? So we have cantilever. And this cantilever is resisting the pressure acting over in this width. That's why, if you further simplify the problem for individual cantilever, then it becomes like this. So we have a cantilever whose length is 2000 millimeters, and then we have here distributed load Q. So how do you calculate Q? So let's try to calculate the maximum Q. Maximum Q is equal to maximum pressure times this spacing, isn't it? 800 millimeters. That's why if I do that, then it becomes it becomes 15.7 megapascal times millimeters. Okay, and this is equal to, so let's change this unit to Newton per millimeters. Then this is equal to what? 15.7 to the 10 to the power of 6 Newton per by the way, sorry about it. This is 15.7, sorry about it, millimeter square times millimeters. That's why it's equal to 15.7 Newton per millimeters. Okay, sometimes it's confusing even for me, but if you use megapascal and millimeters, we don't have to worry about this unit. So we can obtain these units automatically here. Okay, now we have this problem. At this point here, so we have maximum value is 15.7 Newton millimeter, and here it is equal to 0. So now let's try to solve for the reaction moment. Okay, so now let's use the force equilibrium. If you use force equilibrium, then we need to have the force, let's say, the reaction R, and then moment M. First, let's try to calculate the reaction. The reaction is equal to the area of the distributed force. So a half times 2000 times the 15.7. This is equal to a half times 2000 times 15.7. This is force equilibrium. Now we have 15,700 Newton. So now let's calculate the moment. So moment is equal to what? So moment is equal to, so we need to consider the resultant. The resultant is equal to the reaction component. So R times what's the point of the reaction? The arm length. Arm length is what? in the case of a triangle, this is a third. So a third of 2000. This is equal to a big number we have. So 10, 466, 667 Newton millimeters. This is the moment. Okay, so now let's determine the cross section. So anyway, my normal stress should be calculated by the bending moment divided by the section modulus, isn't it? It should be equal to or less than the allowable strength value. So we have the moment for 66667 divided by allowable strength. Where is the allowable strength? Is 8 megapascal. So 8 megapascal. And then this is my section modulus. So what we have to do is we just calculate this number and then find a cross section which is satisfied this section modulus. Then how do you calculate the section modulus in the case of scale section? Scale section, we need to consider the second moment of inertia, and because this is square be force, and then the maximum distance is a half of b. Okay, so that's how we can determine the size of the cross section. Do you have any questions for this example? Okay, so let me talk about the general procedure regarding the beam problem. Okay, first let's consider simply supported beam. For example, let's consider simply supported beam here, and then we can consider some, the force system. Then we can develop the shear force diagram. This is shear force diagram, and then also we can construct bending moment diagram. Look, so once we have bending moment, for example, we can measure bending moment at various positions. Let's say this is x-axis. At different positions, we may measure, we may read different values of bending moment. Let's say we are interested in this maximum bending moment. Then if you're interested in this, then my bending moment divided by the section modulus should be equal to or less than the allowable strength value. And then, which means my section modulus must be greater than or equal to the moment divided by the allowable strength value. So once we have this information, then we check the design handbook for cross section, for square or rectangles or I-shaped sections. Okay, so we check the various cross sections to find, a section which satisfies this condition. Okay, of course the choice of cross section depends on other parameters too. But if we talk about the determination of the cross section from the bending moment, then we follow this procedure. Okay, that's why it is very important to understand how to construct the bending moment diagram. Before we construct the bending moment diagram, so we don't know what is the maximum bending moment for the design of the cross section. What is the design? In the case of design, we have to determine the material and then cross section for given condition. That is the design. Also, sometimes we have to determine the whole geometries. For example, length, and then the cross section, and also we have to choose proper materials. That's why to finish the design, we have to start the design procedure by introducing some, a certain kind of material into my design. Okay, once you determine the type of material that you want to use, then we can calculate the minimum cross section required for that choice and for the given loading condition. And this is the design procedure. Do you have any questions? Okay, so let me stop today's lecture here. Because the remaining stuff is the shear stress. Actually, discussion of shear stress need many consideration, and that would exceed the hour of this class today. That's why let me stop my lecture here at this moment. Okay? See you next week.